morning all. We are on module 4 of chapter 13, magnetic effects of electric currents. Today we will discuss about right hand thumb rule that is given by Maxwell, and it is also known as Maxwell right hand thumb rule or corkscrew rule. In this rule, what we do, you have to hold a conductor in your right hand in such a way that your thumb is in the direction of current and your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. Suppose if you know the direction is the current is flowing in the upward direction, then you have to keep your thumb in the upward direction with folded fingers and then open your fingers and then make a circle. Then in which direction your fingers are moving, this is the direction of the field lines of the magnetic field. So in right hand thumb rule, what you will do, you will keep your right hand thumb in the direction of current, and then your fingers will tell you about the direction of magnetic field. In this diagram you can see the current flowing in the direction of the thumb, or you can say the current is going from right to the left hand side. So what you will do, you will keep your thumb in the direction from right to left and hold the conductor in your hand. Now if you move your finger, then finger curls in the direction of magnetic field. Basically you are moving your fingers in the downward direction. So this is the direction of magnetic field. You can see that magnetic field lines represent itself in a concentric circles. So you can see in the diagram that the direction of magnetic field is given to you. So first is magnetic field due to current through a straight conductor. Suppose you have taken a copper wire, then it is a straight conductor. So you all know that when we pass current through a conductor, it produces magnetic effect, and this is known as electromagnetism, that electricity produces magnetic effect. So if we take a straight conductor and passes electricity through it, then it produces magnetic effects, and if it produces magnetic effects, that magnetic effect produces magnetic field lines. So if the conductor is straight, the magnetic field lines for a straight conductor is concentric circles. You can see in the diagram. These concentric circles become larger as we move away from the wire. It's very simple to understand. If something is not in the magnetic field of the magnet, that magnet do not exert magnetic force on that object. But if anything is under the magnetic field, then there is strong magnetic force. Magnet exert more force. So if something is with the proximity to the magnet, then the more magnetic force will be exerted on that object. And if something is beyond the magnetic field, then very less magnetic force will be exerted on that object. So what does this implies? That if we move away from the wire, and now wire is acts as a magnet, because electricity produces magnetic effect. So when you move away from the magnet, magnetic force gets decreases. So when magnetic force decreases, that the magnetic field lines that are representing itself in a concentric circles, these circles gets bigger and bigger. What does it mean? It means that magnetic force gets weaker and weaker. So the circles becomes larger when we move away from the wire, when we move away from the magnet. Here is a diagram shown to you. Next, magnetic field due to current in a straight long conductor. So this is an activity. Take a thick copper wire and pass it through a horizontal cardboard as shown in figure. Pass a strong current through the wire. Sprinkle iron fillings on the cardboard around the wire. Tap the cardboard gently. You will see a pattern as shown here. You may plot the fill lines with a compass needle also. So the magnetic field lines are in the form of concentric circles near the conductor. Away from the conductor, the field lines tend to be elliptical due to combined effect of earth magnet and mag field due to the conductor. The direction of magnetic field lines resolves with the reversal of the direction of current in the conductor.